Hello, hello. It's been a while since my last video, but here we are again. We are back at it with some more some maths videos for the first time on this channel. So the topic that I want to cover today is something that's really, really important to VCE Maths Methods Units 3 and 4, and that is the topic of anti-differentiation. So my plan for this topic is to first make two videos. The first on anti-differentiation, which is this one, and then do another one about definite integrals, where I give it more intuitive definition of what a definite integral actually is and how do we actually go about calculating these for functions. But in this video, I would like to give you an idea of what an antiderivative actually is. So in order to understand what an antiderivative actually is, or the process of antidifferentiation rather, it is essential that you guys know what a derivative is. So the process of differentiation, taking a derivative of a function. If you are not familiar with that, I will upload a set of notes that I made regarding that topic, and I'll also try and make a video regarding the same thing and post it on the channel at some point. But for this video, we just need an understanding of what taking a derivative actually means, i.e. finding the instantaneous rate of change of a function at a particular point. There's more details regarding that in the notes that I will post along with this video. But when it comes to anti-differentiation, believe it or not, adding the word anti in front of differentiation simply means the process of undoing a derivative. So the process of undoing a derivative. Anti-differentiation just refers to the process of undoing a derivative. So just like when we did our mathematical operations like addition and multiplication, the opposite process of addition, so to speak, is subtraction, and the opposite process of multiplication was division. By analogy, we have the process of differentiation, and the opposite process of that is anti-differentiation. So the whole idea is undoing a derivative. More strictly, it refers to the process of determining a function given its derivative. So if we have the derivative of a function, if we have the derivative of a particular function, the process of anti-differentiation will help us find the original function. So to make this a little bit more concrete, let me consider a particular function g of x, right? G of x. I'm working in complete generality here. We will get into specifics eventually, but we have some function g of x, and I will define this g of x to be equal to the derivative of some function f of x, big F that is. So in other words, g of x is defined as the derivative of capital F of x. So there's no way to prove this. This is just a definition that I have made up in my head, if you like. Right. Well, what if I want to find the antiderivative of g of x? Well, the antiderivative of g of x, I will just introduce the notation here, antiderivative of g of x with respect to x. So antiderivative with respect to x. Antiderivative of g of x with respect to x. The way we denote this, the way we write this in maths is the following. We put a little snake-looking symbol here. We write our function that we want to take the antiderivative of. In this case, it's g of x. Antiderivative of g of x. And we also need to include a very, very important piece of this antiderivative, which is the variable with respect to which we are anti-differentiating. So antiderivative of g of x with respect to x. So we are anti-differentiating with respect to x. So we have to include dx here. So this is a very, very common trap that I see students fall into, and that is that people just write this without a dx. This, as it stands, the expression in the red doesn't really have any meaning. So essentially, this snake symbol is always accompanied by d something. Typically, it's x, but you might see y or z or any other letter. You've got to be careful about that. Okay, well, you might ask me, hey, Si, how do you go about computing this? How do you actually work out what the antiderivative of g of x is? Let me tell you, it's not that difficult given our definition of g of x, which is the derivative of capital F. So every time we see an expression like this, we need to ask ourselves, what function do I need such that what function do I need in order to undo this derivative? So what function will I get if I undo the derivative in this function g of x? So if I write out g of x as the antiderivative as f dash of x, so remember by definition g of x was f dash of x. If I write that out, f dash of x dx. Now think about what this is doing. This is just saying, hey, if I undo the derivative that's sitting on here, that's sitting on this function here, this is the derivative of the function capital F. If I undo that, if I remove the derivative, what do I get? Well, hopefully it is quite obvious here. If not, please try and convince yourself that this is the case. But this is simply f of x. F of x. There is a little bit more coming, but we will get to that in a moment. But f of x, because we have to remove the derivative. We have to undo the derivative on the f dash of x. Another way to think about it, loosely speaking, is that this snake dx cancels out any derivatives over here. So you're just left with f of x, but we're not done yet. We have an additional piece which we really have to take into account. Whenever we're taking an antiderivative, a general antiderivative, we have to add a constant of antidifferentiation. So the c here, c is a constant. Typically, it's called constant of integration. And the key thing to note here about the c is that this c is a real number. It's a real number. So it's just like any other number that you've dealt with before. So pi or 1 million, or it can be anything. Typically in problems, you will be given some conditions which allow you to find the value of this constant c. But you might be asking, why do I have to include this constant here? What happens if I don't, right? Well, loosely speaking, you have to add the constant here because think about it. If you have to differentiate the function f of x plus c, the whole point is g of x was defined as f dash of x. Now, the whole idea is if I differentiate, i.e., if I take the derivative of f of x plus c, I should get back my g of x. So all I've done here is I have done an antiderivative, which means I have reversed the process of differentiation. Now I want to show you that if I apply my derivative again to the result, I should get back what I started with. So remembering our additive rule of taking derivatives, we just take the derivative of each of these terms and then add them together. So the derivative with respect to x of f of x is just f dash of x. That's fine. But the derivative with respect to x of c is just equal to 0 because c is just a constant. The derivative with respect to x of a constant is equal to 0. That's just by the definition of taking the derivative taking the derivative of a constant. Well, so in other words, there's no way to tell once you've differentiated whether or not you had a constant to begin with, because eventually you will have differentiated it out, so to speak. So it's always essential to include a constant of integration for while you're doing an antiderivative. Okay. So C is an arbitrary constant. Typically in problems, like I said earlier, in problems you will be given conditions which tell you which give you some information which allows you to then work out what the value of C is for that specific problem. But we will cover more on that in the coming videos. In general, what we have is if we have a function g of x, if we have a g of x that's equal to something, it's a function of x raised to some power r, where r is not equal to -1. Well, the antiderivative of this follows a very simple formula, a relatively straightforward formula. If we have a function that looks like this, then the antiderivative of g of x, an antiderivative of g of x, don't forget the dx, is equal to an antiderivative of x to the r dx. Now, what this expression on the right-hand side essentially is if I take the derivative of whatever comes out of this expression, then I should get back x to the power of r. So essentially, if I do my maths, say, if I do my algebra and I get some function of x, if I get some function of x, and then I take the derivative of this, then I should get back my original function. So let's see this with an example here. So if I have if my g of x was x to the power of 1, which is perfectly fine, r is not equal to -1, so x is just equal to 1 here. Now, the whole idea behind this, if I want to find the antiderivative of x with respect to x, well, the way I would think about this is this, if I work this out, I get some function of x. If I differentiate that function of x that I get from here, I should get back x. So I'll give you a few seconds to think about what kind of function you need in order to get x. So what you need to do here is to note that f of g of x equals x is a straight line graph. When we take the derivative of a quadratic function, so something of the form x squared, we end up with linear. The derivative of a quadratic function is a linear function. So this should be something like x squared. This should go as something like x squared. But hang on a minute. If I take the derivative of x squared, I get 2x, which is not quite what I want here. I want x. So in order to cancel out that factor of 2 that I get when I differentiate, I need to put in a factor of 1/2. X squared on 2, and then I'll add my constant here, plus c. And please don't forget to specify that c is a real constant. Good. Let's do something similar for x cubed. Oh, actually, let's do something for x squared, the antiderivative with respect to x of x squared. I'll give you a few seconds to work this out. Assuming you've had a go at it, we do exactly the same thing. So this is a quadratic function. If I take the derivative of a cubic function, that's when I get a quadratic function. So my function should look like x cubed. But if I just take the derivative, the regular derivative of x cubed, I get 3x squared, which is almost the same as x squared, but not quite. We're out by a factor of 3. So in that case, I need to divide by 3. And then my constant as usual. Hopefully, let's do one more, and then maybe you'll start seeing a pattern. If we have x cubed, well, I need to take the derivative of something that's x to the power of 4 in order to get something that's x cubed. So x to the 4th. But then if I take the derivative of just x to the 4th, I get 4x cubed, which is almost what I want, but there's a factor of 4 there, which I don't really need. So I can just divide things by 4 and then add my constant. Okay. Hopefully you're starting to see some sort of pattern. So every time I do my antiderivative, all I've done, this is x to the power of 1. This is x to the power of 2, x to the power of 3. So the antiderivative of x to the power of 1 with respect to x was x squared on 2 plus c. So I've added 1 to the power here. So this you can write as 1 plus 1. 1 plus 1 is 2. Surprise. 1 plus 1 on 2. And then this, similarly for the second line, you can write this as 2 plus 1. Actually, you can write this as 1 plus 1 as well in the denominator, 1 plus 1. And you can write this as 2 plus 1. And then similarly, we have 3 plus 1. 3 plus 1 is 4, so that's fine. So in general, if we sort of generalize this expression here, we get something like this. If we have x, an antiderivative of x to the power of r, where r is the antiderivative of x with raised to the power of r with respect to x, where r is not equal to -1. We'll see why in a minute. This is equal to, if you haven't already worked this out, well, here we go. This is the antiderivative of x to the power of r with respect to x is equal to x to the power of r plus 1 all over r plus 1. And remember, r here cannot be equal to -1. You might be wondering, hey, why can r not be equal to -1? I'll give you a challenge to do. Try and plug in r equals -1 into this expression. Let's do it. So we've got r equals negative. If we have r equals -1, we just have x to the power of -1 plus 1 over -1 plus 1. Hopefully you start to see that this is just x to the 0 divided by, oh, we're dividing by 0. Oh no, that can't be happening. So this rule, this sort of generalized formula, does not apply when r is equal to -1, but it works for every other number. You may be wondering, hey, what happens when r does equal -1? Surely I'll be asked to take an antiderivative of that. And the answer is yes. You may be wondering what that is, but the result is quite beautiful. So if we have x to the power of -1 dx, I'll just spoil it for you. This is the same as writing 1 over x dx. if you remember back to your rules for differentiation, i.e. taking the derivative, you may remember that the derivative of some function, something, was equal to 1 over x. Have a think about what that function was. For those of you still wondering, the answer was the natural log, or log base e of x. The derivative of log base e of x was equal to 1 on x. So if I want to undo my derivative, on the log, so if I want to anti-differentiate 1 on x, I should get back the thing that I differentiated in order to get this. So the answer is simply log base e of x plus c, where c is a constant, and I've forgotten to add it here as well, but here we are. C is a real constant, and here r is not equal to -1. Nice. Okay, so that is about all we're going to do for anti-differentiation. Actually, let me quickly go through the properties of antiderivatives, then we will call it a day. So these properties of antiderivatives are relatively straightforward, and I will spend quickly a few minutes just going through these. Properties of antiderivatives. So what do you mean by, you might be asking, hey, what do you mean by properties? So antiderivatives just on their own are quite boring. So we need to be able to figure out what we can actually do with them. So all the kinds of algebra that we can do with them, all the kinds of simplification that we can do. And there are only two fundamental properties of antiderivatives here. And they are as follows. So if we have some function h of x, which is defined as f of x plus g of x, where f of x and g of x are two arbitrary functions that I've just made up in my head here. Remember, this g of x has nothing to do with the g of x I defined upstairs. So if I have a function h of x which is defined as f of x plus g of x, then if I want to take the antiderivative of h of x with respect to x, then this is the same as taking the antiderivative of f of x plus g of x with respect to x. Well, by the properties, one of the fundamental properties of antiderivatives comes right here. This can be split up as the antiderivative of f of x with respect to x plus the antiderivative of g of x with respect to x. And believe it or not, even if h of x was f of x minus g of x, the same sort of property holds. So f of x plus or minus g of x. So this we can turn that plus into a plus or minus. It doesn't really matter whether we have a plus or minus sign. If we just have the sum or the difference of two functions, then the antiderivative of that is given by the sum or difference of the antiderivatives of each of the separate parts of that function. Okay, so that's the first property. So I'll label that as 1. And the second one is a neat little property that I have here. Here, I'll let k be a constant. Let k be a constant real number. So this is not a constant of integration, not the c that we introduced above, but let's just introduce a constant real number. right? Then if we have any function f of x, the following property holds. So if I have some function f of x, then, okay, if I have some function f of x, or any function f of x, we have the following property. If I multiply my constant by my function, and I want to take the antiderivative of the whole thing, well, that's just as simple as taking the constant out of the integrand of the antiderivative sign. Sorry, I won't call it an integrand just yet, but we will get to that terminology in a bit. So I can pull my constant, because k does not depend on x, I can pull it out of the antiderivative sign. So this is just k times the antiderivative of f of x with respect to x. So these are the two key properties of antiderivatives. These are all the things you can do with them. So using these two properties, you can do a whole bunch of stuff with them, and we will cover more of these in the coming videos. In the next video, I'm hoping to cover the principles of definite integrals in the area underneath a graph. So we will establish a link between antiderivatives and something called definite integrals, and go through what's called the fundamental theorem of calculus. So that's a really, really important result that's used in a whole bunch of in a whole variety of areas, including finance and economics and physics and engineering and a whole bunch of other things. But there's more on that in the coming videos. So I will stop here for now. I hope you found this video helpful. If you did, please do reach out to me by email, or let me know what you think of these lessons. Thanks, everyone, and I hope to see you all in the coming video. Cheers.